for all odd natural numbers n, we have that 8 divides the quantity n squared minus 1. So again, to remind you, A divides B implies there exists an integer, and I'm going to call it k, such that B equals AK. Okay, that's what I mean by divides. So let's prove this by induction. We want to make sure that we mention induction somewhere. And then let's say, base case, let's see what happens when n equals 1. Let's prove p of 1. Okay, so let's check, does 8 divide the first odd natural number squared minus 1? Well, let's consider n squared minus 1 when n equals 1 is going to be 1 squared minus 1, which is 0. And 8 does divide 0. Why do I say that 8 divides 0? Because there exists an integer, k, such that 8 times k equals 0. What is that integer? In this case, the integer is 0. This is true because 8 times 0 equals 0. That means that 8 divides 0. It's a little weird. Okay, so now let's do our inductive step. Let's show that P of n implies, and now we have to be a little bit careful. Do we want to say that we're going to prove this for the nth odd number or for the odd number n? Well, I've written this in a slightly mysterious way. I've said for all odd natural numbers n. So if I'm doing P of n, the next step is not P of n plus 1, but P of n plus 2, right? Because I'm not trying to show this for even numbers, and if n is odd, then n plus 1 is going to be even. Now, if that's weird, something you can do is you can say, well, let's do this for the nth odd natural number, and the nth odd natural number will be 2n minus 1, and then in that case I would do P of n implies P of n plus 1, and that would be indexing the odd numbers by n. But this is slightly different, okay? So I want you to see that we can do this using the same inductive principles, but with a slightly different setup. So again, this is because we're dealing with odd numbers. Remember, an odd number plus 1 is even, and we don't want that. So that's why we have an odd number plus 2 to get to the next odd number. All right, so our inductive step, we want to show that P of n implies P of n plus 2. So let's start with P of n. P of n says that 8 divides n squared minus 1 for some odd number n. Well, this means there exists an integer k such that what? N squared minus 1 equals 8k. All right, now, what would this statement look like for P of n plus 2? Let's do our goal cloud. What is P of n plus 2? Well, it's going to be, I'm going to replace this n by n plus 2. So that means 8 divides n plus 2 quantity squared minus 1. Maybe we should simplify this right-hand side. This is 8 divides, well, let's just leave it like that. Let's leave it like that. So this is our goal cloud. So what we're going to want to do now, if you recall what we do at our amazing cocktail parties, is we consider quantities, right? So now we're going to consider the quantity n plus 2 quantity squared minus 1. And we're going to want to show that that's a multiple of 8. Well, n plus 2 quantity squared minus 1, let's multiply this out. This is n squared plus what? Plus 4n plus 4 minus 1. Okay? So I've just multiplied this out, and I've still got that minus 1 there. Now I'm going to rearrange this, and I've got n squared minus 1 plus 4n plus 4. Okay, if you're a little lost as to why did I just jump from something that kind of made sense to, okay, divisibility, I remember that from a few weeks ago, but now what does 8k have to do with, why are we doing this? Okay, let me try to go slowly from where we started to where we are, and then we'll finish it up. So I want to show that 8 divides n squared minus 1. I'm doing this by induction, which means I want to look at n small and then show that the nth case implies the next case, whatever the next case is. Here, since we're doing odd numbers, if I look at the odd number n, the next odd number is n plus 2. All right, fine. Now, 8 divides n squared minus 1. I'm assuming this. I guess first I checked it for the first odd number. That looks good. Now 8 divides n squared minus 1. I'm assuming this. And I said, well, if 8 divides the quantity n squared minus 1, that means there exists an integer k. So exists a k in z such that n squared minus 1 equals 8k. All right, so that's just appealing to the definition of divisibility that we already had a few weeks ago. And now I'm considering this quantity. Where does this quantity come from? Well, I looked at P of n, and I want to do P of the next case, right? Well, in this case, the next case is odd, so I've got to do n plus 2. So I looked at this very expression, but for n plus 2 instead of n. So here I've got that expression for n plus 2 instead of n. And if you'll recall back, the way that we showed divisibility claims was we said, consider the quantity, whatever's on the right-hand side. That's just what tends to work for us. So now I've considered the quantity, whatever's on the right-hand side. Consider the quantity. N plus 2 quantity squared minus 1. And this is n squared plus 4n plus 4. That's n plus 2 quantity squared. Now I've got this minus 1. And all I've done, I haven't done any factoring or any advanced mathematics. I've just written this thing down in a different order. N squared minus 1 is here. The rest of it is here. Okay, so here, just make sure you're here. I'm going to take a sip of my now cold coffee. Oh, that is some cold coffee. Now, what do I know about this expression? Well, n squared minus 1 is 8k. And I've got 4n plus 4. Let me factor out a 4. And I've got 8k plus 4 times n plus 1. Think for a second as to why this makes us done. Okay, so again, I want to show that 8 divides something. So 8's definitely going to divide this part. Why should 8 divide this part? Well, what's 8? 8 is 2 times 2 times 2. So I need 3 factors of 2. Luckily, I've got 2 factors of 2 right here. I've got 4, which is 2 times 2. So I would win if I knew that n plus 1 had a factor of 2 in it. What does it mean for n plus 1 to have a factor of 2 in it? It means that n plus 1 must be even. How can I know that n plus 1 is even? Ah, that's right. This is an odd number plus 1, which is therefore an even number. Which means that there exists an integer L such that n plus 1 equals 2L. Which makes 8k plus 4 times n plus 1 equal to 8k plus 4 times 2L. If I multiply these two together, I get 8k plus 8L, which gives me 8 times the quantity k plus L. Since k and L were integers, their sum is also an integer, which means 8 divides this quantity, which, as we roll back, is this quantity, n plus 2 quantity squared minus 1, and therefore we're done by induction. Right, this is exactly what we had in our goal cloud. One final induction example. Let's show that for all real numbers x bigger than -1, and for all natural, all non-negative integers n, we have the following. 1 plus nx is less than or equal to 1 plus x all raised to the power n. Okay? So first, we're going to prove this by induction. So proof, we're going to say by induction. And we're going to do the base case. The base case is going to be to check this for our smallest case, which is the case when n equals 0. So we're going to check p of 0. Again, we normally start with p of 1, but we're normally dealing with n being a natural number. But in this case, the smallest n that we care about is n being 0. So let's check. Left-hand side, 1 plus 0x, that's 0 times x. Okay, 0 times x is just 1. And this is less than or equal to, let's check the right-hand side, 1 plus x to the 0. 1 plus x to the 0 is also 1. 1 is less than or equal to 1, so we're good. Now, why is 1 plus x to the 0 1? Because x is bigger than negative 1, so this is a positive number. I've got a positive number raised to the 0 power, which is just 1. All right? We're not messing with 0 to the 0. I don't know what 0 to the 0 would be. So now, let's do the inductive step. Let's suppose p of n is true, and try to show p of n plus 1 is true. Well, p of n is just this thing. So we assume 1 plus nx, I'm going to leave a little bit of space here, is less than or equal to 1 plus x to the n. All right? Now, again, like I said, I tend to have success in induction problems when I think about what I learned most recently. Addition and multiplication I learned before I learned exponentiation. So I want to mess with that right-hand side. Okay? Now, what is p of n plus 1? Let's go over here. P of n plus 1, this is, well, p of n plus 1, this is my goal, is going to be this exact same statement, but for n plus 1. So this is 1 plus, I replace my n by n plus 1. This paper keeps jumping up. 1 plus n plus 1 times x. And I want that to be less than or equal to this statement where n is replaced by n plus 1. 1 plus x to the n plus 1. This is my goal. Goal cloud. All right. Now, like I said, I learned this longer ago than I learned this. So I probably want to mess with the right-hand side. So how do I get the right-hand side here to look like the right-hand side here? Well, this is n plus 1 factors of this binomial. This is n factors of that binomial. If I have n factors and I want n plus 1, I just multiply by that binomial. So I'm going to multiply both sides of this equation by 1 plus x. Now hold on for a second. Why can I just multiply both sides of an inequality by a number? That's not always such a good idea, right? There's a potential that I could flip the inequality. I could have the inequality go this way, right? I start with this inequality, I end up with the inequality going that way. Why do I know this is okay? Again, x is bigger than negative 1, which means 1 plus x is positive. So I'm multiplying both sides of the inequality by a positive number, which means I'm not switching this inequality sign. Okay, now I want to simplify both sides of this, but I'm going to leave a little bit of space here. So I'm going to start by simplifying the left-hand side. So I have 1 plus nx plus x plus nx squared. So that's the left-hand side. And the right-hand side is precisely what I want. 1 plus x to the n plus 1. Now this is not the same left-hand side that I wanted. But let me simplify this left-hand side a little bit. This is 1 plus n plus 1x, just what I wanted. But then there's this pesky nx squared term. Right, this is a 1 plus, okay. This thing is present here, but not present here. But notice I've got n, which is non-negative, and a real number squared, which means this thing is greater than or equal to 0. This nx squared is greater than or equal to 0. Well, if I want this, and I got instead this plus something, why should that be a problem? Because this is bigger than or equal to what I want, 1 plus n plus 1 times x. Look, I've got what I want. What I want is less than or equal to what I want plus something non-negative, which is less than or equal to my right-hand side. Okay, this can be a little confusing, but let's suppose that I need to show you that some amount is less than this. But instead I show you some amount plus something is less than this. Well, then for sure that amount is less than this. Okay, so let's do a little analogy. Suppose I want to convince you that person A is shorter than person C. Let's suppose I want to show you person A is shorter than person C. And I can never get person A and person C in the same room, right? But I happen to show you that person A is definitely not taller than person B, and person B is definitely not taller than person C. Then I've established this relationship, okay? So I used multiplication of the original inductive hypothesis, multiplying the inductive hypothesis by this factor of 1 plus x to get here, which is sort of comparing person B to person C. And then I used just basic logic to compare person A to person B, and therefore I'm done by induction. With this, putting these sides together, I get 1 plus n plus 1x less than or equal to 1 plus x to the n plus 1. And therefore I'm done by induction.